Hello everyone, this video is for EL6303 probability and stochastic processes. I'm going to explain the first two questions of homework 11. Now let's do the first one. Given the stochastic process xt is real with autocorrelation, Rxx tau and the power spectral density Sxx omega, show that its correlation is real and even, and its spectral density is even and non-negative. So here, if xt is real and WSS, we know that its correlation function can be written as Rxs t plus tau t, and by its definition, it's like this, and we exchange the position of these two, we get the formula like this. Then this is Ixx t plus tau, which is Ixx minus tau. So Rxx tau equals to Rxx minus tau, so Rxx tau is real and even. Then to prove density, power spectral density Sxx omega is even and non-negative, by its definition, we take the autocorrelation. We take the Fourier transform of autocorrelation, and here we use the Euler formula and expand this expression. Here is the multiplication of our Rxs and sine omega tau is odd function. So the integral of this term is equals to 0, and then we get this expression, and then this is as xx minus omega. Obviously, it's non-negative, so we get the result. Power spectral density as xx omega is even and non-negative. Now let's do the second question. It is suggested the following function of v, this 3, could be autocorrelation function of a WSS process, or a spectral density function. So let's decide whether which functions can present either or both. By theorem on page 60, the power spectral S omega, the power spectral density S omega of a WSS process, whether it's real or complex, it's non-negative, which means S omega larger than 0, as we discussed before. And then the second one, the autocorrelation function RT1, T2 of a process, whether it's real or complex, it's non-negative definite function. So to solve this problem, we should determine whether these three functions are non-negative, or and its Fourier transform is also larger than 0. So let's do the first function. It's an exponential function. If we let this function as autocorrelation, then we find its Fourier transform is 2 over omega squared plus 1. Obviously, both of these functions are non-negative, so this function could be autocorrelation. Then we let this function as the S omega, and we could get its inverse Fourier transform is 1 over tau squared plus 1. Obviously, these two functions are larger than 0, so the exponential function could be power spectral density. So we find the conditions are satisfied, so this exponential function can represent both autocorrelation and the power spectral density. Now the second function, we can write it like this. Actually, it's square of sinc function, also the sa function. So if we let this function to be autocorrelation, obviously it's larger than 0. It's not negative, and its Fourier transform is like this. Here omega, the absolute value of omega less than w, so this term is larger than 0, so the whole spectral density is larger than 0. So this is sa squared function could be autocorrelation. Then we let this sa squared function to be power spectral density, and we can get its inverse Fourier transform. It's like this. Here tau is less than alpha, so this term is larger than 0, so the whole r tau is larger than 0. So both of these functions are larger than 0, are non-negative, so the sa squared function could be power spectral density. So we find conditions are satisfied, so this function can be present both autocorrelation and power spectral density. Now let's do the third function. Firstly, we let this function to be autocorrelation. Its r tau is non-negative, but its Fourier transform is a sa function. We know sa function can be less than 0, so as omega is not satisfied with the condition as omega larger than 0. And if we let this function to be power spectral density, we can get its inverse Fourier transform is also a kind of sa function. Obviously, it's not always it's not always negative, so this function cannot be power spectral density. So we find since we know sa function is not non-negative, so the conditions are not satisfied. Thus, this function cannot present either autocorrelation or power spectral density. This is all for today. Thank you.